Welcome to Cambridge IGCSE Physics, Lesson 29.1, Action of Lenses. Today we explore how lenses interact with light beams, focusing on converging and diverging lenses. This is core content for your physics examination, covering fundamental optical principles that apply to cameras, telescopes, microscopes, and human vision. Understanding lens action is essential for both theoretical knowledge and practical applications in modern technology. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, describe the action of a thin converging lens on a parallel beam of light. This means explaining how parallel rays are brought together to a focus point. Second, describe the action of a thin diverging lens on a parallel beam. This involves explaining how parallel rays are spread apart, as if coming from a virtual focus. Third, understand focusing and spreading effects. This includes recognizing the difference between convergence and divergence of light rays. These objectives align with Cambridge IGCSE assessment requirements and form core knowledge for your examination success. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, converging lens, pronounced converging. This is a lens that brings parallel rays of light to a focus point. The lens is thicker in the center than at the edges. Second, diverging lens, pronounced diverging. This lens spreads parallel rays apart as if they came from a virtual focus point. The lens is thinner in the center than at the edges. Third, parallel beam. This means light rays traveling in the same direction, with rays remaining the same distance apart. Additional terms include focus, which is the point where rays meet or appear to meet, and principal axis, the central line passing through the lens center. Understanding these terms precisely is crucial for examination success. Let's explore converging lens action. The fundamental principle states that a converging lens brings parallel rays of light to a focus point. This happens because the lens is thicker at the center than at the edges, causing light to bend inward. Key features include the lens shape is convex, meaning curved outward. Parallel rays entering the lens converge, meaning they come together at a single point. The focus lies on the principal axis, which is the central line through the lens. This is a real focus because rays actually meet at this point. The diagram illustrates this clearly. Notice how parallel rays on the left enter the lens and bend towards the principal axis, meeting at the focus point F on the right. This convergence is the defining characteristic of a converging lens. Now we examine diverging lens action. The fundamental principle states that a diverging lens spreads parallel rays of light apart. This occurs because the lens is thinner at the center than at the edges, causing light to bend outward. Key features include the lens shape is concave, meaning curved inward. Parallel rays entering the lens diverge, meaning they spread apart after passing through. The focus is virtual, located behind the lens where rays appear to originate. This is called a virtual focus because rays don't actually meet there, but their backward extensions do. The diagram shows parallel rays entering from the left. After passing through the lens, they diverge outward. The dashed lines show virtual rays extending backward to meet at the virtual focus F. This spreading effect is the defining characteristic of a diverging lens. This comparison table highlights key differences between converging and diverging lenses. First, shape. Converging lenses are thicker at the center than the edges, while diverging lenses are thinner at the center. Second, effect on rays. Converging lenses make parallel rays converge or come together, while diverging lenses make them diverge or spread apart. Third, focus type. Converging lenses have a real focus where rays actually meet, while diverging lenses have a virtual focus where rays appear to originate. Fourth, symbol. Converging lenses are convex, curving outward, while diverging lenses are concave, curving inward. Fifth, common applications. Converging lenses are used in magnifying glasses and cameras, while diverging lenses are used in spectacles for short-sightedness. Sixth, ray behavior. Converging lenses bring rays together, diverging lenses spread them apart. Understanding these differences is essential for examination success. Ray diagram construction follows specific rules for accuracy. For converging lenses, first, draw parallel rays horizontal to the principal axis. These represent the parallel beam of light. Second, show rays bending towards the axis after passing through the lens. This demonstrates the converging effect. Third, all rays meet at the focus point on the principal axis. This is where convergence occurs. Fourth, use solid lines for real rays because light actually travels these paths. For diverging lenses, first, draw parallel rays horizontal to the principal axis, just like converging lenses. Second, show rays bending away from the axis after the lens. This demonstrates the diverging effect. Third, use dashed lines for virtual rays that extend backward to the virtual focus. These show where rays appear to originate. The diagrams illustrate both cases clearly, showing the fundamental difference in ray behavior between converging and diverging lenses. Experimental demonstration proves lens action principles. The apparatus needed includes a light source to create the parallel beam, both converging and diverging lenses for comparison, a white screen to show ray behavior, and an optical bench for precise alignment. The method follows these steps. First, set up the light source to produce a parallel beam of light. Ensure rays are traveling in the same direction. Second, place the converging lens in the beam path. Position it perpendicular to the light direction. Third, observe convergence on the screen. You'll see rays meet at the focus point, creating a bright spot. Fourth, replace the converging lens with a diverging lens, keeping the same setup. Fifth, observe divergence. Rays spread apart after the lens, and no focus appears on the screen. Safety is important. Avoid looking directly at the bright light source to prevent eye damage. Results clearly show converging lenses focus the beam to a point, while diverging lenses spread the beam apart. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, describe what happens when parallel rays hit a converging lens. Think about the ray behavior we studied. How do parallel rays change direction? Where do they go after passing through the lens? Question 2 is intermediate level. It states, explain the difference between real and virtual focus in lenses. Consider which type of lens produces each focus type and what makes them different. Question 3 is advanced level. The question is, draw ray diagrams showing parallel beam action for both lens types. This tests your ability to construct accurate diagrams following the rules we learned. For all questions, remember to use correct scientific terminology like converge, diverge, focus, and principal axis. Draw diagrams with straight lines and arrows to show ray direction. Take time to think through each answer systematically. Lens principles power countless modern technologies. In cameras, converging lenses focus light from objects onto the digital sensor or film, creating sharp images. The lens system controls how light rays converge to form the picture. In telescopes, multiple lenses work together to gather starlight and focus it for observation. Large converging lenses collect faint light from distant stars and planets. In microscopes, lens systems magnify tiny objects like cells and bacteria. Converging lenses create enlarged images for scientific study. In spectacles, both converging and diverging lenses correct vision problems. Converging lenses help far-sightedness, while diverging lenses correct short-sightedness. Career connections include optical engineering, where professionals design lens systems for various applications. Photography relies on understanding lens behavior for creative and technical work. Astronomy uses advanced lens systems in telescopes and space instruments. Medicine employs lenses in surgical microscopes, endoscopes, and diagnostic equipment. The principles you learn today become tomorrow's technological innovations. Let's review the solutions to build confidence. For question 1, the answer is, parallel rays converge after passing through a converging lens, meeting at the focus point on the principal axis. This demonstrates the fundamental action of converging lenses. For question 2, we distinguish between focus types. Real focus occurs when rays actually meet at a point, which happens with converging lenses. Virtual focus occurs when rays appear to come from a point but don't actually meet there, which happens with diverging lenses. For question 3, accurate diagrams should show parallel rays entering the lens, correct lens shapes, convex for converging, concave for diverging, proper ray directions after the lens, and correct focus positions. Now for exam success strategies. First, understand command words. Describe means state the features you observe. Explain means give scientific reasons why something happens. Second, draw clear diagrams with proper labels and arrows showing ray direction. Third, always state the lens type and describe ray behavior precisely. Fourth, remember the real versus virtual focus distinction. This is frequently tested. Let's summarize today's essential learning. The key points to remember are, first, converging lenses bring parallel rays to a real focus point. The lens is thicker at the center, causing rays to bend inward and meet at a point where they can be detected on a screen. Second, diverging lenses spread parallel rays apart as if coming from a virtual focus. The lens is thinner at the center, causing rays to bend outward, and the focus point is virtual because rays don't actually meet there. Third, ray behavior determines lens type. If parallel rays converge after the lens, it's converging. If they diverge, it's diverging. This fundamental difference drives all lens applications. For further study, practice drawing ray diagrams accurately using the rules we learned. Review how lens shape connects to ray behavior. Convex lenses converge, concave lenses diverge. Prepare for the next lesson on image formation by lenses, which builds on today's foundation by exploring how lenses create images of objects. Master these basics before advancing to more complex optical systems.